Hi, everyone. Mr. Geiselman here. We're going to get started with our next lecture on graphing distance versus time. So yesterday you should have went over some of the stuff on velocity and know that velocity is equal to distance over time plus a direction. Today we're going to get going with graphing that and how that looks as a graph. So distance over time is what we're working with today. So a quick refresher from yesterday, we need to again talk about motion because we're going to be graphing motion today. So motion is defined by a change in position measured by distance and time. So we're going to be today looking at graphs that have changing distances or changing position, all right, over a certain amount of time. And that's what graphing velocity is all about, distance over time, right? If you're in motion, you're moving. And our unit for this most commonly is going to be meters per second, but we could also have miles per hour, kilometers per hour, feet per second. All of these different things could be our motion units, right? And motion, again, is any change in distance over time. So quickly refresher on velocity. Velocity is equal to that speed or that rate of change in position over time, all right? Plus the direction that we're going, right? So I am moving at 50 meters per second north. I'm moving at 3 meters per second south. I'm moving at 5 meters per second west to the left. All right. So velocity always has that direction in it. And that's why we're able to use it when we're talking about graphing. Right. That equation there again, V equals distance over time plus a direction. So today when we look at things, we're going to be looking at graphing, and a quick refresher on graphing. Hopefully you remember this from math class and other science classes you've taken. Graphing has an X and a Y axis. Our Y-axis up here at the top, right, is our vertical axis. It runs up and down. So our y-axis is this one on the vertical axis. So this is where we're going to put distance. So distance will go on our y-axis. So if we ever, when we do distance versus time graphs and we're graphing velocity, distance will go on the y-axis. The x-axis is the horizontal axis. It runs down here at the bottom. All right. So we're going to always graph time there because time goes on and on and on. And it makes it a lot easier for us to graph time on the x-axis because we can't stop time. An important thing that I didn't put on the slide, we do need to give our graph a title. Distance versus time, for example, for our next graph that we're going to look at. That's a perfect idea. And we also need to label what we're in. So if we're putting distance on our y-axis, are we measuring distance in miles, feet, meters, kilometers, right? What unit are we using? So we label it. And down here on the bottom, are we measuring time in seconds, hours, minutes? What are we using? Then we have to properly space out and label our units. Is each line 5 meters? Is each line 10 seconds? And then properly spacing them out for the rest of the graph. So I have an example here. All right. Johnny runs around a track or a 400-meter track once. He runs the first 100 meters in 10 seconds. He takes 25 seconds to run from 100 meters to the 300-meter mark. And he runs from the 300-meter mark to the finish line at 400 meters in 20 seconds. Let's graph his motion, right? We have 3 distinct parts to this graph. First off, I labeled my graph, distance versus time, and then I labeled my axes. So my y-axis is where I put my distance. I'm measuring distance in meters, and then I labeled my line. So every line is 50 meters. Down at the bottom, I labeled my axis, my y or my x-axis, excuse me, or the horizontal axis is measured in seconds, right? So it's time measured in seconds. And then each line is 5 seconds. And I labeled 5, 15, 25, 35, 45, right? And I skipped right here would be the 20 mark. But because it gets a little messy, I just left it out of there. And you know that each line is 5 seconds. So if we look his first data point, he ran the first 100 meters in 10 seconds. So I went to the 10-second mark, and I went up to 100 meters, and I put a data point there. And I drew a line from his starting position to that position. I would have used a ruler, but the smartboard was being really finicky. Our lines should always be really nice and straight and neat, and rulers do that really well. It helps us determine the slope and see that in a graph much better. The second data point then said he made it to the 300 mark in 25 seconds. So what's 25 seconds from 10 seconds? Well, you add 10 plus 25, you get 35. All right, so I'm going to the 35-second mark, and I knew I was at the 300 meter mark. That's where that belongs. There's my second data point, and now I drew a line. And if we had a perfect line here, you could see that our slope changes slightly, and we'll get into exactly how much it changes in a second. And then our third data point, he gets to the finish line, which is at 400 meters. So I go to 400 meters, this line up here. And how long does it take him? We said it takes him another 20 seconds. Well, if we add 25 seconds, 25 seconds, onto 35 seconds, we get 55. And here we go. And this is where this data point is. And we draw another line. Again, if we used the proper tools and the smartboard wasn't being a little finicky, you'd see that there's a distinct change in all those lines as far as the slope goes. But that's how our graphs should look. Now, when we talk about slope, slope is the incline, the gradient, how steep our graphs are. And when we look at that, we're really looking at the rise over the run, or how fast the rate of change in the y-axis over the rate of change in the x-axis. We do that by denoting a y2, the ending unit on the y-axis, and we subtract that from the starting unit, y1, right? And then we do the same thing with x2 minus x1, right, to find our rise and our run. Hopefully that's review for math class, but we're going to go through a little practice problem with it. When we talk about slopes, right, positive slopes mean we're moving away from that 0 point. We're moving up and out. A positive slope means that we have a speed that we are moving away from home. If the slope is constant, right, it's not changing, that means we have a constant speed. And if it keeps on getting steeper and steeper and steeper every increment, that means we are going faster. A negative slope means we're moving from the top of the y-axis back down towards the x-axis. This means we're moving back to our starting position, or if you think about home, we'd be moving back to that starting position. A constant slope, again, means that we're moving at a constant speed or a constant velocity, and the steeper the slope, the faster it's going to be. If we have no slope, right, or a zero slope, right, we have standing still and there's no motion, right? If there's 0 for the slope, the rise over the run is equal, all right? We have no slope, we have 0 speed. And the blue, the further away from 0, then the yellow further away, or the orange, So the further away we are from the 0 mark on the y-axis, the further away we are from the starting position. So if we look at our distance versus time graph from the example before, we can take a look at this in terms of slope. So from the 0 to 100 meter section, our slope, or our velocity, because slope is equal to velocity, is equal to the 100, which is our y2, minus our y1, which is the starting point, 0. So 100 meters minus 0 divided by the run, right, along the x-axis of 0 seconds and 10 seconds. So 10 seconds minus 0. And if we get 100 minus 0, we get 100 divided by 10 minus 0, 10. 100 divided by 10, we have 10 meters, right? Because we have meters up top and seconds on the bottom. We get 10 meters per second. We can do the same thing for the 100 to the 300 meter section. Again, now we take 300 minus 100, y2 minus y1, and divide that by our x rise, or our x run. So 35 seconds minus 10 seconds. And if you punch that into a calculator, we'll get an answer in meters per second, because the meters and the seconds don't cancel out. And that simplifies to 8 meters per second. So the slope is slightly flatter. right? It's not quite as steep as that first section. And then our final section is the 300 meter to the 400 meter section. Slope is equal to velocity again. So velocity is equal to 400 meters minus 300 meters divided by 55 seconds minus 35 seconds. Those are y2 minus y1 over x2 minus x1 values. And when you do that equation, you solve for that equation, you get 5 meters per second. All right, hopefully you can remember that slope is equal to velocity, and velocity or slope is equal to the rise over the run of the graph. We always put our x-axis on the bottom, and that's where time is going to go for our distance versus time graphs. Distance is going to go on the vertical axis or the y-axis, and we're always going to need to label our axes, whether we're measuring distance in meters, feet, miles, kilometers, or we're measuring time in seconds, minutes, or hours. All right. Let us know if you have any questions. Have a great day, everyone.